Okay, this is done in a slightly different way using screen record, so I can use some of the animations. Let's see if it works. We're going to talk about intrinsic semiconductors and the electron. Well, the electron, basically something that hangs around on the outside of an atom, circulating around. At the top you have a full outer shell, and at the bottom you have a not full outer shell, such as in sodium. And we're going to discuss why one is an insulator, the top, and the other is a conductor, i.e. the bottom. We also have to know the electron is a very small negative particle, which is, well, 1/2000th of the mass of a proton. Little things like that we have to know because they get asked all the time. Now, if you put an overall charge on such an apparatus, on the metal at the bottom, you can see that the electrons can drift from one to another, drift away, you see, and that's conduction. Any movement of charge is conduction, so it's electron movement. Whereas an insulator at the top, there's nowhere for the electrons to go. They cannot go from one place to another because they've nowhere to jump into. So even if they're just as close and they've just as much will to do it, there's nowhere to go, so they can't jump. Whereas the electrons, obviously at the bottom, the metals, have space to jump into, so they can move. There you are. It's also sort of like, a bit trippy staring at this for too long. But I will persist for a little bit longer. Now we have to talk about what is conduction then. Well, conduction, as I've said on several occasions, is when charge moves. So if you have electrons which are actually free to move, this is a wire, by the way, this is meant to represent a wire. Inside the wire, if it's a metal, because of the fact they're dissociated, the electrons aren't necessarily attached. These little electrons are free to move. So if you put a positive and a negative, they'll go away from the negative and towards the positive. This drift from negative to positive is what we call electric current. There you are, they're all drifting in that direction. So when the individual electron is free because he's not necessarily associated with a nucleus of an atom, because there's a kind of an overall orbital which allows them to move from one place to another. And this kind of like electric movement, this electric charge, can be ions in a liquid, it can be lots of things, but in a metal it's the movement of electrons. It's also the movement of electrons in a semiconductor, but in a slightly more complicated way. So let's look at silicon. Silicon is in group 4, and like carbon in group 4, it has 4 electrons in its outer shell, and just like carbon, it can form 4 bonds. So it can share its 4 outer electrons with 4 other silicons to form a crystal of silicon. I mean, we used to say that it was possible to base life on silicon as well as carbon. We're carbon-based, but silicon can also happen. So if we bring in the 4 other silicon elements, each one of them, as you can see, shares an electron pair in a covalent bond. And these covalent bonds completely surround the silicon, go on forever, and form a crystal of silicon. Now there's other ways to represent these. You can represent them as a pair of electrons, or in chemistry it can also be represented as a pair of lines showing that there's a shared bond between them. So these are all ways of representing the silicon crystal. But for our method, I'm going to show the silicon crystal like this. Now each one of those blue balls is in fact a silicon crystal. It's pure crystal, which is why it's given the name intrinsic. Intrinsic just means pure. So this is an intrinsic section of the course, the pure silicon section of the course. And as you can see, each one of these little silicons is fairly close together. It's almost as close as in a proper metal, but there's 4 covalent bonds holding them together and no way that the electrons can move around because there's nowhere for them to go. And then in comes a piece of energy. And this piece of energy hits one of the electrons. And this electron is emitted. Now, this emission is because all the energy of the wave comes to just one electron. And we'll talk about this when we come to the photoelectric effect. But it frees the electron. And this electron can now move around, causing conduction of electricity. Watch it again. I love that animation. There you are. One more time, shall we? Yeah, one more time. There we are. That is the transmission of electricity. So when we take silicon crystal, we have all the little crystals laid out like that, all nice and neat, with the bonds between them, the covalent bonds. If we heat them up, we create an electron-hole pair. That's an electron and a hole it left. And the more heat, the more electron-hole pairs are created. Now, if I therefore put a charge across this so that there's a positive and a negative, the electrons will move towards the positive. And this will be seen as a flow of electrons. So, to recap, what's actually happening is electrons are being produced by heat, which creates electron-hole pairs. And if you have more electrons, you have more current, which gives you less resistance. So, resistance is varying according to temperature, and we call such a device a thermistor. Now, it's a thermistor in its resistance is dependent on temperature in a different way from metals. You see, a metal, the resistance increases with temperature, but a thermistor, it decreases. This is a picture of a thermistor, and you can see the symbol, which looks like a variable resistor with a hockey stick instead of an arrow through it. And that gives the symbol for thermistor. It can be used to measure temperature. It can be used to turn on and off electric devices, particularly digital devices, such as electric fires, things like that, to keep a room warm, or fire alarms when it comes to too much heat. So a thermistor, tremendously useful device used in most ovens these days. Light dependent resistor used in street lights. This is still a piece of intrinsic semiconductor. That's still just pure silicon in a little row at the top there. But what happens is the more light energy that falls on it instead of heat, that changes the resistance. So this changes its resistance based on the light energy falling on it, because the light energy is making electron-hole pairs. And these electron-hole pairs, the more they make, the lower the resistance, the more conduction. So when it's dark, its resistance is high. But when it's light, the resistance basically decreases, because there's more electron-hole pairs which are free to conduct the electricity. Rather simple, really. Now, the next thing we have to look at is how this can be represented graphically. How can we draw a graph of both the two types of semiconductors? So we'll start with the light-dependent resistor. And what we're actually going to do is plot a graph of resistance against energy. In this case, the amount of light energy coming into the light-dependent resistor. And as you can see, more light energy, less resistance, which is the opposite of a metal. And a thermistor behaves in exactly the same way. The more heat energy, the less resistance. So a metal has the opposite effect. This is the experiment which will tell us this. This is what you've done, the variation of resistance of a thermistor with temperature. The thermistor is placed in glycerol. Glycerol has a very low specific heat capacity, so that it spreads the heat evenly because of its low heat capacity. And the thermometer, therefore, and the thermistor, we assume, are at the same temperature. So we simply heat up the water or cool down the water, and we look for the different resistances at different temperatures so that we can plot a graph. Plotting the graph, or a calibration curve as it's sometimes called, is the aim of the entire exercise. Now, we don't want to get too hung up with the method. Basically, you write down what you do, taking the temperature at set intervals and plotting a graph of the temperature against the output, the resistance. Now, far more important than the method, of course, are the precautions. You heat the water slowly, you use glycerol. Now, you don't have lag in this experiment, but you do have the glycerol, which is a tremendously important part of it. So, to recap, an intrinsic semiconductor is pure silicon. We create electron-hole pairs with heat, which can then conduct electricity. In the next section, we will talk about extrinsic, which are things which are being doped, which I hope is not applying to you.